All right. Good morning, everyone. If you're watching the video here today, we're going to be talking a little bit about an introduction into harmonic motion, and specifically looking at pendulums, and one of the handouts that's going to go along with that. So you can watch this before working on that handout, and then when you're done, reference back to that handout. We will cover some of the things in there, and then you can work on that after the conclusion of this video. So far in units 1 through 5, we talked about motion, energy, momentum, forces, all those things. Last unit, we talked about uh, fluids, and you notice even with fluids, we dealt with forces and dealt with energy. And so now we're going to be talking specifically about a type of motion that we'll see occasionally, and that is harmonic motion. And what we mean by harmonic motion is motion that is repetitive, that is occurring again and again and again. It follows a specific pattern. And one of the things that's required for harmonic motion is typically some sort of restorative force. So there are a few types that we'll look at in particular for this unit. And the first one we're going to start with, probably the easiest to see and identify some pieces of it, would be a pendulum. So here we have a pendulum, and we can bring that pendulum back, and when we let it go, it swings back and forth, right? So here is our pendulum. Let's go slow. And as it swings back and forth, we see a number of things. So what we're going to be doing here is we're going to be describing some of those properties, what makes this motion special, what makes it unique, and then eventually, how do we graph some of those values, right? What does that all look like? So before we dive too deep into graphing the values, there are a few things that we want to think about when we talk about harmonic motions. The first is there must be some sort of equilibrium position. And so for our pendulum, our equilibrium position is going to be represented by this dashed line right in the middle. If we take this pendulum and start it out at the equilibrium position, there's no force acting on it, and it's just going to stay there. Nothing happens. But when we displace or move something away from the equilibrium and let it go, then it's going to begin to move. And it's going to oscillate or swing back and forth to the left and to the right of this equilibrium position, this middle position. And anytime it moves off to the side, there's always going to be a restorative force. So for example, when we're over here right now to the left side of our pendulum, we know that this tension, yes, there's some tension pulling it up, counteracting the weight of the object, but also there's a tension pulling it in towards the center of the circle, or not circle, in towards the equilibrium positions. Let's see if I can. I don't know if I can draw on the, I can't. Okay. That's okay. We can do this. We'll do this laser. Nope, I can't do the laser pointer on the, okay. So I can't seem to annotate on top of my embedded thing, which is okay. That's all right. So we see that this pendulum here is being pulled at the moment to the right. So it is being pulled to the right here. Yeah, oh, that's okay. To the right, back towards that equilibrium position, back to the middle. And then anytime we swing over to the other side, we are now pulled to the left, back towards the equilibrium position. So always being pulled back to that middle, back to that central point. And we've looked at things that have gone under this type of motion before as well, notably a spring, right? So when you stretch out a spring, we know that spring is pulled back to where it was before it was stretched. Or if we compress it, we know it's pushed away. And we even have an equation for springs that we've used before, right? So if we had a spring, that's here. So here's our spring. If we had an equilibrium position here at this point, say this was our unstretched length, we stretch it out a little bit more. We know that there is now a force, so it's stretched out to the right, but we know that there's a force that's going to be pushing it back to the left, back to the middle. And if you compress it, if we're to compress that spring here, we know now the spring would be pushing an object back now to the right, back to the equilibrium position. And we had what we called Hooke's law, a formula we've seen a few times before when we talk about the force of a spring. We said that force was equal to negative kx, k being our spring constant, x being how far something is stretched or compressed. And we've already seen this equation. This is not a new equation before, but what makes this a harmonic motion equation is really the negative piece, right? So the negative is implying that our force is always going to be in the opposite direction of that compression. We're always being pulled back to the middle. And so that's what causes this harmonic motion. Anytime it swings to the right, it gets pulled back to the middle, and then it overshoots it and moves to the left, and then it's going to be pulled back to the middle. And so it's constantly going back and forth and back and forth, always being pulled back to equilibrium. In the absence of friction, of course, it would continue on indefinitely, but we know when there is friction, it's going to slow it down. Eventually, it's going to stop and come back to an equilibrium point. We're not going to look too much at really friction in these type of harmonic motion equations, but that's kind of what happens. So let's look back at our pendulum here. And again, here's our pendulum. It's going to swing back and forth, back and forth, back and forth. Not a big shocker, right? And this is what we're going to do in our lab. We're going to be looking at pendulums and eventually a few of our formulas that represent how this type of motion occurs. Well, when we talk about harmonic motion, there are two terms specifically that we really want to start out and focus on. Terms that you might have seen before or possibly not. But at least this first one, I would expect that we at least have some vague familiarity with, and that is frequency. The other term that's going to be really, really closely related is the period of motion. So these are two terms that we will use to describe sorts of harmonic motion, right? So what is frequency? Frequency is the rate of how many cycles there are in each second. So this is cycles per second. So in other words, if we were to start a timer and I were to time 1 second on this pendulum back and forth, and I were to count how many times it completes its back and forth motion in 1 second, that number would be the frequency. How many times does it repeat its motion in 1 second? So a thing like a pendulum typically is going to have a relatively low frequency. It takes a while. Right now it's going in slow motion to slow it down a little bit, but typically a pendulum's not going to have a huge number of back and forth motions per second. Imagine you on a playground swinging back and forth. You probably don't even complete one full back and forth motion in a second, right? So for some harmonic motion, the frequency is going to be less than 1 cycle per second. Our unit here is cycles per second, but we typically don't say that. We typically are going to use Hz or hertz, He like the car, right? Hertz. So hertz is going to be our unit of measurement for frequency. It's really just number of cycles per second. How many complete back and forth motions would that occur? And so what is a cycle, right? We need to know what a cycle is. Well, for a pendulum, it's one complete motion. The portion of that motion that's going to repeat again and again and again. It is not just from left to right. That's not a complete motion. It is when we let it go, when it gets back to where it began, where it resets, where it starts that motion again, would be that complete motion. So I'm going to let it go. We're going to start our timer. It's going to go to the right. Still going. This is still the first cycle. It's going to swing all the way back. So now we're going to the left. And then we're back to where we started with, right? And so that's one cycle. And then it's going to do that cycle again. So it goes to the right. And then it's going to swing back to the left. And when we go all the way back to the beginning, that is one complete cycle. For a cycle, we don't have to start it all the way on the left. We can really time it at any point here. It doesn't really matter. So for example, let's say we'll watch the motion. Let's start the cycle now. So it starts out in the middle. It swings to the right. Now it's going to the left. And so it's back in the middle here. And you might think, oh, well, it's back in the middle. That's one cycle. But if we look at that motion, it started in the middle. It swung to the right. Now it's swinging back to the left. It's not going to repeat that motion yet. This is actually only half a cycle. And so it's going to swing off to the left and then back to the middle. And that is going to be one cycle. So that's one cycle there. Let's watch one cycle again. We're going to swing to the right and then all the way back to the left, pass through the middle, And that's one cycle. So let's speed it up just a little bit to make it. So let's go. Let's count our cycles here. All right. So what would a cycle be if we go from the middle? So start 1, 2, 3, 4, 5, 6. So our cycle is every time it passes through the middle, it swings to the right, to the left, and then back to the middle. And then it's going to repeat that motion again and again and again. And we can start a cycle really at any point. We just have to track out that motion and see, where does that motion repeat itself? That's going to be one cycle. All right. That's going to be one complete cycle. So period is really, really similar to what frequency is going to be described here as, where frequency is number of cycles per second. Period is going to be the number of seconds per cycle. So you'll notice these are related to each other. They are reciprocals of each other. So you'll see in your formula sheet, we do have a relationship between period and frequency. And the equation is really, really simple. We could write this one of two ways. Typically, I write it as frequency. Let's use a different color than blue. Let's go red. Frequency, which we'll represent with F, is 1 over, so the inverse of, or they're reciprocals of each other, cycles per second and seconds per cycle. And then period. Well, we can't use P for period. We use P for pressure. Rho, which was kind of a Greek P, was for density, recently from last unit. Lowercase p we know is momentum. And so we're not going to use either of those. Period is really a time measurement, right? Seconds per cycle is typically going to be measured just in seconds. How many seconds did it take to complete one cycle? So it's a time measurement, not the total time, but the time for one complete rotation or one complete back and forth motion. And so period we're going to represent with a capital letter T because it's essentially a time measurement. You could also write this as period equals 1 over the frequency. Both of these are fine, but they are reciprocals of each other. So if I know the period, I very easily know the frequency, right? And so period is the number of seconds per cycle, and our unit of measurement is just going to be seconds here. So let's get our stopwatch out. If we were to get a stopwatch, we are going to start the time right at the beginning. So it goes all the way to the right. It's going to swing all the way back to the left. And then we're going to stop the stopwatch. So once it completes its motion, that time right there, 1.38 seconds, that would be the period, how many seconds there are per cycle, right? And these are related to each other. For example, if our period was, let's say, 2 seconds per cycle, that would mean it takes 2 seconds for one cycle to complete itself. We know the frequency would be the inverse of that, 1 over 2, which makes sense, right? If the period is 2 seconds, so 2 seconds for one cycle, we know that one cycle will be completed in 1 second, only half of the cycle will be able to be completed if it takes 2 seconds for the full cycle to be finished. So this is frequency and period and our pendulums, right? Before we move on to our graphs here, and I'll go a little bit with that, I want to briefly look at this motion. So if I think about a pendulum is essentially a back and forth motion. If I draw that out, back and forth, back and forth, back and forth. If we were to take this motion and plot it throughout time as we go back up and down, back and forth, we're going to find a similar shape. We're going to find some side of sine or cosine curve, right? It's going to go up and down, up and down, up and down, with an equilibrium position being in the middle. So anytime we're graphing out harmonic motion, and we're going to look at on the sheet you have force, acceleration, position, and velocity. We'll look at all those things. What we're going to find is it's all going to be sine or cosine curves, depending on where we set our starting point at. And so how do we equate these, right? We have some equations for these values, and you might recognize these from your math class, but we're going to be a little specific. So if I wanted to find the position at a specific time period, and these are on your formula sheet, you won't really use these too much in the quest or anything like that, but it's good to know. I think sometimes they show up a little bit, but not too often. What is our sine and cosine equations? Well, we're going to start with the amplitude. Amplitude is how far above or how far below that equilibrium line this curve is going to go. And so A is going to be our amplitude. And if we're graphing position, what we really mean here is maximum position. How far to the left or how far to the right does that pendulum go? Position is going to end up being a cosine graph. And then it's cosine of what? 2 pi times the time. So what time we're looking at, divided by the period, divided by 1 complete cycle. All right. We can find this also and relate it to angular velocity as well. You'll see it written a few different ways occasionally, but this would be an easy way to write it. The other version of this equation would be if we wanted to write this in terms of velocity. So velocity at some time period, because we know that the speed is going to go increase and decrease. Speed is at 0 at the peak and at the bottom, so the crest and the trough, the top and the bottom, or on our pendulum, we know our speed is 0 when we're all the way to the left or all the way to the right, and our speed is the greatest when we're back at 0 position. So our velocity graph is going to be actually a negative value, negative, because of that harmonic motion, negative maximum velocity, so V max, times, whoops, times not cosine, but sine of, and then the same thing, 2 pi, and I'm writing with my mouse, so bear with me here, times the time at some period, divided by the actual period of motion. So both these formulas here, you won't see them too often, but in case you do, they are relating position and velocity to these graphs, right? Whoops. There we go. Okay. All right. There's one other equation we're going to look at, and this is what you're going to do in the lab mostly. So we'll really investigate this equation in lab, and that is specifically for a pendulum. There are a few factors that affect the period of the pendulum. Take this down a little bit. And so here would be the equation for the period of a pendulum. And this is what you're going to look at in our lab. You'll also see a similar equation for a period of a mass spring oscillator. So not only do we have a period, but we could also have a mass spring. And a mass spring oscillator is basically right here what happens when we connect a mass to a spring and it swings back and forth. So I'll call this, I think has it listed on your formula sheet. I think it just says period, and then it just says spring. I don't think it gives you anything more than that. So I'll write period of a spring. So the P is for pendulum. Period of a spring is a slightly different equation. And so what is our equation here for period of a pendulum? Well, it's really simple. Equation is going to be 2 pi. All right, and then what we're going to have from here is it's going to be 2 pi times the square root of the mass. So, oh, whoops, I have that mixed up. That is our mass spring system, sorry. 2 pi times the square root of L. L in this case is going to be the length of the pendulum divided by G, gravity. The equation for the spring is going to be 2 pi square root of M mass over K spring constant. All right, so this is our equation here for these setups. Really, this is an angular velocity equation. I'm not going to worry too much about deriving this equation out, but we can talk about that a little bit more in class and when we get to our wave equation. It's kind of a velocity is frequency times wavelength piece a little bit. But we'll look at that later. These are our big equations. And in the lab, we're going to use specifically this L over G, the pendulum equation. All right. Okay, so those are our equations. These are the main ones that you'll see. One of these two describing the period based on the mechanical structure of either the pendulum, the length L, length of the pendulum, G, gravity 9.8, or if it's a mass spring system, like right over here, a mass swinging back and forth across an equilibrium point. Then we get this 2 pi squared of m. That would be the amount of mass on the spring, and then K, the spring constant K. All right, so let's take a look now briefly, and I'm not going to do necessarily all of these. It's kind of maybe an exercise for the reader, but we'll take a look briefly at these. There we go. Okay. So on your paper, you should have a number of graphs, position, velocity, acceleration, and force. I'm going to briefly look at this, and we'll see. Our equation has a pendulum with the pendulum over here on the right side. Left side is A. The middle we are describing as point B. And the right side, when the pendulum's over here, we'll call that point C. And it asks us to graph the force, acceleration, position, and velocity. Well, I'm going to really quickly do just like the first, let's do B, C, A, or sorry, B, C, B. That's how it goes. That's the order. B, C, B, A, B. And so why is there so many B's? Well, that's what the pendulum does, right? It goes from B over to C, and then back to B, and then over to A, and then back to B, then over to C, and so it's back and forth, constantly passing through that middle point. So let's look real briefly here at a few of these graphs. The first one we'll take a look at is the very top one, which is force F, right? So what's the force? If we start out at B, right in the middle, we should know that the force at B is 0, right? Every time I'm right in the middle, we are at equilibrium position. We're not being pulled in any direction. So our force is 0. What about when we are over here at C? When I'm over here on the right-hand side? Well, which way are we being pulled? We're being pulled back to the middle, always back to equilibrium. So in this case, to the left. So we're going to call that a negative force. I'm just going to put a negative value down here. All right. And then what happens? It's going to swing back to B. And once we're back in B, which way are we being pulled? Well, we're back in equilibrium. So what's the force at equilibrium? 0. You might see a pattern from here. Then we're going to swing over to A. And what is our force when we're at A? Well, back to equilibrium, back to the middle. When I'm over on the left-hand side, F equals negative kx, right? There's a restorative force. So I'm back to the right. So I'm going to see a positive value. And then we're going to go back to B. And so we go back to B, and this is our force graph. We see something that looks like this. You see a similar curve, and it's going to continue on that repetitive pattern again and again and again and again. Right? So that's going to be what our force graph would look like. The next one is acceleration. All right. And I'm not even going to bother redrawing this because we already know F equals m times A. And so what does that equation tell me? That equation tells me that force and acceleration are directly proportional. Meaning when force is 0, acceleration is going to be 0. When force is positive, acceleration is going to be positive. When force is negative, acceleration is going to be negative. When force is at a maximum, acceleration is going to be a maximum. So where is our force and acceleration the greatest? The same spots that the force, same spot was before. So when we're back in the equilibrium, no acceleration, no force. When we're over here at C on the right, we know we're being pulled to the left in the negative direction. So we're going to have a negative acceleration as well. We're going to accelerate to the left. So the force and acceleration graphs actually are completely identical to each other. There's no difference between these whatsoever. And we know Newton's second law, F equals ma, it's going to kind of describe that for us, right? So that's why we have that equation there to help us out. All right. We've already got 2 graphs done, and y'all can track out the rest to get a little bit of a practice on identifying that. We've got 2 more, and that'll end up this video. All right, so the next one is position. Position should be the easiest one to identify. It just says, where is it? So we start out at B. Where are we at B? Our position is in the middle. So we are at 0 position. What about C? We swing out to C. Now we're to the right. So what's our position? To the right. It's positive. Then we go back to B. So our position is back to 0. We swing over to A. We're to the left. So a negative position. And then again, we go back to B. So back to 0. And you'll notice something about this graph. It's a mirror of the force and acceleration graphs. Remember, one of our restorative force equations was F equals negative kx. So what's the negative mean? Well, that means when our force is positive, our position is negative. When our position is positive, our force is negative. They're opposites of each other, right? That's what makes it a restorative force. So F and X are opposite signs of each other. All right, and we're going to have one other equation we'll look at, and that is velocity. So V for velocity. So let's think right here. We're going to start out at B. Well, B might be a little bit tricky. We're not sure, but I know when we pass through the middle, right? Let's watch it on normal. Let's watch what happens when we swing it back and forth. Where is this pendulum going the fastest? Well, the pendulum's actually going the fastest when it passes through the middle, right? You can also think about it in terms of energy, right? We're at maximum potential energy when we're way up at a point, and then we convert it to kinetic energy with maximum kinetic energy when we pass through the middle. So our maximum kinetic energy is going to actually be the middle position. So where are we at B? Well, we're at B moving to C. B to C. So that's at B. We're at the middle. Are we moving to the right or the left? Since C comes next, we know we're moving to the right. And so I'm going to start out with a maximum positive velocity here. And you might now start seeing why the position graph is cosine and the velocity graph is sine, right? Although it does a little bit depend on where our origin point is. These are offset by a bit. So it's moving to the right. So it starts with maximum positive velocity. And then what happens next? It swings over to the right. When we're all the way at position C, that's when we're changing direction. And our speed is going to drop to 0. And then what happens next, right? Next, we're going to move back to the middle, but now we're going to move to the left. And we're going to move the fastest to the left when we hit B again. So we're down here now. And then what happens? We swing over to A, stop at that height. And then we swing back to B, moving to the right now, so maximum positive velocity. And so we see this graph is going to look like, let's try that again. It's going to look something like this for our velocity graph. Offset a little bit, right? So we have force, acceleration, position, and velocity graphs, all different a little bit. And you certainly want to know when in a pendulum is it moving the fastest? When is it moving the slowest? When does it have the greatest position, the greatest acceleration, greatest force? And certain graphing, it helps us identify those, but really knowing when and where the maximum and minimums are for each of these variables, I would say is something you want to specifically take a look at. So now you have worksheet 711. Hopefully this video kind of guided you through some of that. Maybe you were working along with it, or maybe you haven't started it yet. Go ahead and go through that worksheet. It's going to view a lot of the things that we just talked about. And then next class, when we're together, we are going to do our lab, and our lab's going to be about pendulums, and it's going to be specifically about this equation. So you're going to have to measure a pendulum, measure the period of a pendulum, and see if our length here makes an effect or not. It should, right? Our length should make an effect on the pendulum. So we'll see how it does. Does this equation work out the way that we expect it to, right? Okay. So hopefully this was a helpful video to give you an introduction into harmonic motion. Have a great day.